Hello there everyone and welcome to another UILCS video. In this video we're going to cover the red-black tree in Java. So, what is a red-black tree? Let's just focus on the definition real quick before we get into all those words. A red-black tree is a balanced binary search tree that uses coloring to balance itself. So as you can see here, I have a mock image of a red-black tree. You can see that it follows typical binary tree structure, right? Smaller children of the root node are on the left. Smaller children of the parent are on the left. Larger children of the parent are on the right. Right? You can just see that mimicked here. So it follows binary search tree behavior, but it also has these colors, right? We use these black and red colors to balance out our tree. If you remember from our AVL tree video, the binary search tree has a, fault where if it becomes severely unbalanced, it can essentially act like a linked list, which is bad for time complexity and efficiency. So a red-black tree is essentially just another way to balance your tree. So let's go over the 5 or 6 rules of a red-black tree. So the first rule is that nodes are either red or black. As you can see here, I have black nodes, red nodes. We don't have any like orange nodes. No. Oh, well, that's a lot. No, you only have red or black nodes in a red-black tree. The root is always black. So your first element, no matter what, will always be black and always must be black. Null children are black. So what is a null child? Well, when I have a tree, right? Let's just draw like a normal tree. We said that this tree, or the children of our leaf nodes are like null, right? Because by default, this 5's left pointer is null, and this 5's right pointer is null, and this 15's left pointer is null, and this 15's right pointer is null. So that's what a null child is. It's basically just the left and right pointers of a leaf node. And we said that these are black. So in a red-black tree, this would have a black null node. You'd 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 have a black null node. You would have a black null node. You'd have a black null node. And you'd also have a black null node. So I'll just fill those in with the paint. Boop, 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 boop. And I'm making them squares because that's how I learned it, just drawing them as squares. Because it's important to know that these null black nodes exist. The next rule, and this is one of the 2 most important rules of the entire tree, so I'm going to underline this. I'll do it in like yellow because that's different. Black height is maintained. So let's go over height. So we said in the binary search tree video that height starts at 0, so the root node has a height of 0. Then your first level, height of 1, second level, height of 2, and so on and so forth. Well, your black height represents the amount of black nodes, right? So you could say, okay, this is 0, ignore you, this is 1, and then this is 2. So it's basically like normal height only, right? It's basically like the normal height that we did, but we kind of ignore all the red nodes when we're calculating height. Okay, so let's actually go through this and show how black height is maintained in this tree. Alright, so this is a height of 0, we skip the red node, height of 1, height of 2. So this branch is good, this section is good, this has a height of 0, skip, height of 1, height of 2, this is 2 as well, height of 0, skip, 1, 2, 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 and then 0, skip 1, 2. So as you can see here, throughout the tree, no matter which branching path you take, the black height is always 2 from your root node to your null child, right? Null children are black. That was the rule right here. So thus we have to count them when we're looking at black height. I mean, you can skip them if you want, I guess. I don't think. Well, no, just count them. Yeah. Okay. The next rule is that nodes are inserted into this tree by default red. So if I was here, right, and I want to insert a node, let's say 1, it would just be 1. It'd be red like this, right? Nodes are by default inserted red. And then the last rule is, and oh, let me just show you real quick. Because this node will have its own, it has no children, and we said its no children are going to be black. I'll fill that in. Even though we added this red, black height of 2 is still maintained. 0, 1, 2. Right? 0, skip, 1, skip, 2. 0, skip, 1, skip, 2. So a black height of 2 is still maintained. That's partially why we allow ourselves, or just say inserted nodes are red, because that means they won't mess with the black height and we won't have to worry about that. Now, this is the second very fundamental and important rule to understand. A red parent cannot have a red child. So what does that mean? Well, let's go back to our example here. Let's say, okay, actually I'll leave this one empty. So I'll give it back its null black child. So let's say I want to insert 0 into this tree, right? 0 following normal binary search tree behavior would be inserted right here, and then we said that inserted nodes are going to be red. So we would insert this as red. Give it our value of 0. But just through this process, we've broken this rule, right? Because look, here we can see our parent of 0. This is the parent. The parent is red. And then the child 0 is also red. You can also view it as subsequent red nodes. Excuse me. Thus, a red parent does have a red child in this case, and we've broken this rule. And I mean, this makes sense if you're looking at the whole idea that coloring serves as a way to make a balanced binary search tree, right? Because is this tree balanced now? No, it's not balanced, right? This is left leaning. So this is just the example, right? But okay, then what happens, right? Because obviously I want to insert nodes into this tree, and by the rules, they have to be inserted as red. Then how do I avoid a double black, or sorry, how do I avoid this double subsequent red situation? Let's go over insertion. So here I have an example of a red-black tree where I've inserted 7. As you can see, after inserting 7, we have a double red error, right? This doesn't fit rule number 6, one of our two most pivotal rules. Thus, we need to fix this. How can we fix this? Well, the first thing you need to notice when you're dealing with insertion and fixing this double red error is the color of your uncle. So what is the uncle node? Well, looking at the newly inserted node, looking at 7, we can say that 7's parent is 8. The sibling of 8 is 11, and thus the uncle of 7 is 11. So that is what we mean by uncle. So in this particular instance, we are dealing with the red uncle case. Just write it out. the red uncle case. So when you're dealing with a red uncle, we will take the parent, or we're going to do a process called recoloring. That's a term you might hear when talking about red-black trees. All that means is we're focusing not on rotation or anything, but just simply changing the colors associated with these nodes. So the parent and the uncle are going to be turned black, and then the grandparent, which in this case would be 10, is going to be turned red. But I want you to notice something about this tree. Can we make this 10 feasibly red? No, we can't, because this 10 represents our root node. And we said in rule number 2, the root must always be black. So this is what I mean by must be black, right? We have to enforce the blackness of the root. So let's do that. Let's follow the red uncle case. So this is our tree initially. I'm going to recolor. I'm going to say recolor via red uncle. And then, so let me take this tree, let me copy and paste it. So this node will be black. You'll also be black and you'll stay red. And let me also, or you'll stay black because you're the root node. Otherwise, we would have made it red. And let me draw in the null children. Because as we're learning the red-black tree, I want you to remember that these null children are black and they exist. So let's count, and instead of black height, everything still met that this red uncle case works. Let's run this through all of our rules. Our nodes are either red or black. That one is true for this. The root is black. That is also true. Null children are black. That is also true. Black height is maintained. Let's figure that out. So 1, 2, skip tree. 1, 2, skip tree. 1, 2, tree. 1, 2, tree. 1, 2, tree. So black height is maintained, so we're good. Nodes are inserted red. Yes, this 7 was inserted, and it was inserted as a red node over here, which is why we had to do this whole recoloring. And then lastly, a red parent cannot have a red child, our second pivotal rule, and this is true. There is no red parent that has a red child in this tree. Thus, we have proved that the red uncle case and the steps according with it are accurate. Okay, so now that we've covered the red uncle case, I want us to look at this red-black tree. So as you can see, the node that we've inserted, or I guess I should make it more clear, we've inserted 7 into this red-black tree, and because of this, we have created a double red error. Remember, because we inserted 7, whenever we insert a new node into a red-black tree, it is red. Right? So that's why 7 is red, and that's why this double red error exists, right? Basically just rule 5 and rule 6. They work in tandem with each other. And of course you can see we have null black children from rule 3, I'm pretty sure. Yeah. Rule 3, null children are black. This is explaining that stuff. And sorry, this also has a null black child, and so does 7. I'm going to draw the null black children this year not exist. So, what I want you to pay attention of is who is the uncle of 7? Well, 7's parent is 6, and 6's uncle is this null child, which is black, right? So if we were to fix this double red issue, we're going to use the black uncle case. The black uncle case. So in the black uncle case, so the first thing we're going to do is perform left right or right left rotation to linearize the tree. So what is linearization? So what does it mean for a tree to be linearized? Well, I want to show you this, right? This is a non-linearized tree. If we were to draw the ancestry path of this leaf node here, you'll see that we have to take a turn with change direction. In a linearized tree, there is no change of direction. A linearized tree will look something like this, for instance, right? If you were to draw the ancestry path, there is no change of direction and it looks like a straight line. Thus, it is linearization. Next, so if we did left-right rotation, we're going to perform left-left rotation. And then if we did right-left rotation, we're going to perform right-right rotation. And then we're going to take the old parent and make it black. And the old grandparent. Let me fix this up a bit. Grandparent. We're going to make it red. And when I refer to old here, I mean like post-linearization. So with post-linearization, what is the parent? What is the grandparent? I'm not saying like post left left, post right right rotation. No, it's basically the parent and grandparent after this step. Okay. So this is the rotation that we need to do, and this is the recoloring that we need to do. So now with our steps laid out, let's go about, well, doing it. So step one, we need to linearize this tree. We have, it goes left, right, so we're going to perform a left, right rotation. Excuse me. Let's add in our children. I don't want you to ever forget about the black null children's existence. That's very, very integral to like the red-black tree as a whole. So now that we have it in this LR form, let's perform left-left rotation. Why? Because I said if we do left-right, then we have to do left-left, or if we had to do right-left, then we do right-right. So I'm going to do left-left rotation. Oh, oops, my fault. Boop, 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 and then boop. So you are gonna be 10, you're 7, you're 8, you're 6, and you're 12. And then now, lastly, we have to do our recoloring. I'm going to say we're going to recolor via, I looking don't like the way this R and E are looking, so let me rewrite that. Okay, that's just even more chopped. That's always fun. Recolor via black uncle case. Which will give us what do we say? We said at this point after left-right rotation, right? For in terms of our recoloring, we look at this section. So the parent is going to be this. The grandparent is going to be this now. So this is our parent, this is our grandparent. And we need to make 7 black. So we'll have a black 7. Let's draw that in right now. And we need to make the grandparent, which is 8, red. So I'll make you a red 8. And then everything else can stay the same. You're going to be a nice red 6. And then you two are just going to stay the same. Because remember that even though we're drawing like the whole tree here, we're really focused on the area where the issue is occurring. So this section of the tree. We're looking only tree nodes at a time, which is you also saw this idea in the AVL tree video, right? So let's fill in our colors. And now let us check our rules. So are all nodes either red or black? Yes, all nodes are either red or black, and our final answer is the root black. Let's see. It should be over here somewhere. Yeah, the root is black. Are all null children black? Well, of course, because null children are just black by default. Is black height, is black height maintained? Excuse me. 1, 2, 3, or 1, 2, skip tree, 1, 2, skip tree, 1, 2, skip tree, 1, 2, skip tree, 1, 2, 3, 1, 2, 3. Black height is maintained. And then other nodes that we considered red. What that means is it's not saying that this initial 7 should be red in our final outcome. That 50 rule is just saying whenever we insert a node, it should be initially red. Okay? And then the 6th rule is just, do we have any subsequent red nodes like we did here in our final tree? Well, no, we don't. There's no red parent, red child node pairings here. So we're good. So this is a completely fixed red-black tree using the black uncle case. So this was insertion. Now I would like to move on to deletion. So I'll remove this. Now for deletion, before we begin deletion, I want to introduce the idea of double black. This. So when I have a red-black tree, right? Maybe it looks something like this. This red, this black, right? So maybe I have a tree like this. And this tree could have any values, like maybe 10, 15, 8, and 4. That's not important. Let's say I removed this node entirely. What happens to the tree? Right? I remove this node and now we're left with a tree that looks something like this. 10, 8, 15. And sorry, of course we also have I'll draw in the little black children. So 8, 10, 15. What I want you to notice in these trees is that we have actually lost the black height. Before we had a black height 1, 2, 3, 1, 2, 3, that was good. One skip. Oh, I guess this tree is a little bit invalid low key. I should probably fix that. Let's make this like a node. Let's make this a black node so that we can maintain our height. And I'll call this like 9. And then it'll have its own, it'll just have black children. So add 9 back into the equation now. On this side, so I'll draw in 9. I'll draw in its black children. So I have the habit of just making not valid by red-black trees. It's just a problem. There we go. It's valid. Now that's a horrid 9. Let's make a 9 look better, guys. Okay, there we go. That's good. So, like I was saying, 1, 2, 3, 1, 2, 3, 1 skip 2, 3, 1 skip 2, 3, 1 skip 2, 3, 1 skip 2, 3. So we had a black height of 3 everywhere. Life was good, right? Let's check on a new tree. 1, 2, 3, 1, 2, 3, 1 skip 2, 3, 1 skip 2, 3, 1, 2. What has happened to this node? Because we got rid of this black node, we effectively lost a black height along, alright, let me use yellow because the color I've been using, along this path. We've lost a black node here. Here's along this path. Regardless, so we've lost one black height. So what we say this empty node, here, what would I need to make up for, right? If this has a height of 1, 2, 3, if all these have a height of black height of 3, this has a black height of 2. If instead this symbol, this singular black node counted as 2 for the black height. If it was double black, you could even say, then we would say this is tree. So what we like to do is we say that this black child is forced to be double black. It has double blackness, right? The only way for this tree to be balanced is if this one black child counted as 2 black nodes, if it was double black. And that's a problem. We do not like double blackness in our tree. We want double blackness to be removed whenever we handle deletion. So with that explained, let's talk about a really simple thing. Before we jump into the actual complicated cases, I'll just write it. I'm not going to do any examples, but deletion of a red node functions just like binary search tree deletion. So I'm not going to draw that out because you should know binary search tree after watching the binary search tree video. So I don't think I necessarily have to explain that one. But what I do have to explain are a multitude of black, or what I do have to explain is what happens when we delete a black node. So for our first look at deletion of a black node, I want to delete 8. So I want to get rid of 8. And I just want to make this point clear that this is red. There's a edge coming out of it. This whole section is supposed to be a smaller section, or like a subtree and a larger tree, okay? This is not the root node. But anyways, I want to delete 8. Currently, we have a black height of 1, 2, 1, 2, or sorry, skip 1, 2, skip 1, 2, skip 1, 2, skip 1, 2. Once I delete this 8, and it just becomes a single black node, so it looked like this. You'll see that we'll have skip 1, 2, skip 1, 2, skip 1. Right? So in order for this tree to meet rule 4, which said black height must be preserved, this node has to be double black, which I'll indicate by circling it. And thus we have double blackness, and what I say about double blackness? It's bad and we want to fix it. So in this particular case, this is the case we use when we have a black, I call it black black. So when we have a black sibling and both of its children are black, right? Look, we had a black sibling, 12 was black. 8 and node we deleted had a black sibling, and both of its children were null, so they were black. So we have black sibling. When you have, or I'll just say, right here, black sibling and children. So what we do here is we're going to do a recolor. Right, we're going to recolor some of these nodes. We're going to do a recoloring. So we're going to take our sibling and we're going to make it red. And then we're going to make our parent and then we're going to make it black. Why am I doing black and red? That's it for the black black case. So if I were to copy this, we end up with a tree that looks like this. This is going to be black, right? And then this is going to become red. That's good enough. So let's count our block height now. 1, 2, 1, skip 2, 1, skip 2. So it's good everywhere. And what I also want you to kind of visualize, right? When I say make this parent black, we're trying to make it black such that we can like remove this double blackness property. You can kind of say we're passing along, this is supposed to represent 2 black. We're passing along 1 black to the parent. And because our parent was red, that 1 black will make it black, okay? And the reason I bring this up is what if our parent was black? Well, when we try and pass up our black, okay, we'll pass up, I guess, the blackness, so this will have 1 black. But now this was already black. We're adding another black, so now has 2 black. This is double black. So even though this is fine, this is not fine, right? Even though black height, I guess, is preserved, we have double blackness, which is never allowed. We're not allowed double blackness. I look, you should add that as a rule. But I think it's fine here. So what would we do in this situation? We'd recursively go up to the next situation. We recursively go up, because I said this is a sub tree, right? This is a part of a larger tree. So now we look at 10 and its parent, and its sibling, or whatever, right? Whatever case we need to use. And we'd use that case and we'd fix the tree. Now, actually, I didn't mention this red uncle in insertion. What happens when I guess I couldn't show it in this example, but you know when I said grandparent is red? Well, what if in red uncle this was part of a smaller tree or something? And by making this red, we had a red 10 and then a red note above it. So it looks something like this, right? Now we'd have another double red situation and we'd have to go to we'd have to run a 2 uncle insertion cases on that and see which one would work. I just wanted to make that point clear. So it's a little bit, insertion's a little bit recursive-y. Same with deletion, we're gonna do some recursion in our code. Okay, so this was the black situation, or also known as, I guess, this black sibling in kids. Now, what if you just have 1 black child? So red, black, black, black. So black height is preserved, black is good. 10, 18, 12, 7. 1, 2, 3, 1, 2, skip 3, 1, 2, skip 3, 1, 2, 3. Right, black height is preserved. This is our tree. Let's say I'm going to delete 7. So now, I guess I can just call this I'll call this the red child case. When we have a red child. Right, so, ooh, we gotta move this down. Let me take all this stuff and just, whee! The red child case. So we have black sibling, red child. So what we do in this situation is we first do left-right rotation or right-left rotation to linearize the tree. Hey, where have we seen this before, right? Then we do left-left rotation if we did left-right, or right-right rotation if we did right-left. And here the rotation or the recoloring is a little bit unique. So our old sibling and this is still post linearization. We'll take the color of our old parent. And then our old parent becomes black. And then our old child, so our old, call it the old, I'll say old child, because rotation will change some things around. Our old child will become black. So, and yet again, this is not referring to the first and current tree. This is referring to the tree post linearization. So when I refer to old, I'm referring to it like the post-linearized sibling, post-linearized parent, post-linearized child. Not after we did our right rotation or left rotation, but also not before we did any rotation. So you really have to pay attention to the post-linearization part. Excuse me. So let's do this. Let me take this tree over. I'll draw it over here. So it's low-key a nice short tree, right? And this node's gonna have to be double blacked, right? Because this would have had a height of 1, 2, 1, 2, 3, 1, 2, 3, 1, 2, 3. Deleting this node, which will give us a situation like this. I really shouldn't make these nodes that small. They're all like pretty big numbers. Yeah, 18 is really big, guys. Yeah, like that. Make you black, I'll make you red. So 10, 18, 12, right? Look at this node. Now this has a height of 1, 2, 3, 1, 2, skip 3, 1, 2. So this singular black child is double black, right? It has to be considered double black for us to have, or for us to maintain black height. And sorry that I haven't been drawing in the no black children, but I feel like y'all should know them. Y'all know the no black children are here, and I'm factoring them in when I'm doing my black height counting, and you should as well. But because we're still learning, I'll draw them in here. So what do we say? If we need to linearize, let's do it. We need to linearize. We're going to do right-left linearization. Why? Because we have to go right-left to reach our child. We're trying to essentially linearization, taking this side with the child, right? We want to make sure it's linear. That's what we want to do. The side with the red child. That's why this is the red child case. We kind of focus and care about this red child. So we're going to do right-left rotation. That's going to give us U. You're going to be still U. You're going to become that 12. You're going to become that 18. Now you're going to have two of your own black children. Let me fix this. I don't like it that much. Maybe. Okay, cool. Alright. Give me a second. There we go. That's fine. Mm-mm. Right. So after we do left, right, or right, left rotation, we linearize the tree. Remember when I talk about old sibling, we're looking at this intersection. So the old sibling is you. The old parent is you. The old child is you. Okay. Hopefully y'all can see that that's just from our tree terminology and such. And just the understanding that we're focusing on these tree nodes. So now we're going to perform right, right rotation. Why? Because we said if we're going to do right, left, then we have to do right, right. So let's do that. So this is going to be 12. This is going to be 10. This is going to be 18. Let me wait real quick. Boop, 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 boop. And now I'll make this 18. So what do we say now? Let's do our recoloring. The old sibling, which was 12, will take the old parent's color. The old parent was black. This would have to be black anyway, because now it's the root node. The old parent will be black, and then the old child will be black. So let's see, did we fix our double black error? Is our tree fully, does our tree maintain black height? 1, 2, 3, 1, 2, 3, 1, 2, 3, and a 1, 2, and 3. So that is, oh, oops, the red child case. So let's say we have the following red black tree, right? 18, 10, 26, 23, 24. Everything is balanced. We have a height 1, 2, 3, 1, 2, 3, 1 skip 2, 3, 1 skip 2, 3, 1 skip 2, 3, 1 skip 2, 3, right? So our black height is maintained, everything is good. I delete 10, right? So what happens here? Well, we call this, or I call this red sibling, right? We have the red child, this is the red sibling. Boop, boop, red sibling. Or let me write a case so it sounds cooler. The red sibling case. And I really don't agree with that E. But I don't mind drawing in this line first. But I'll try the E first. I guess the E is fine. Alright. So basically what we do here is we perform or actually we'll start with this. We take the sibling. I don't like that one bit. There we go, I like this better. We take the sibling and make the sibling black. B. Okay, cool. And we make the parent red, and then we perform either left left or right right rotation, and that just depends on like we rotate towards the double black node. Like so if I'm deleting 10, you're going to perform right rotation to rotate towards it. I guess that also makes sense because this is just a simple null node. This has two full nodes and multiple full nodes. So it makes a lot more sense that we're doing right rotation and left left. I just want to explain the logic behind that. We're rotating towards the double black node. That's the official reason behind it. So let's do that. Let's take this tree. I'm going to take you. Very well, before I even do anything, let me give myself some more room down here. And let's go back to our red sibling case. So let's take, I think I only have it copied. Yippee! I don't like doing that. Copy, paste, place. This node is going to go away, right? We're just going to create a double blackness here. And I'll explain why this node is double black for all the other examples. So I'm not going to go over it too much in here again. Right, it has to be double black so that it can resize double black, because the only way to maintain black height is if this was double black. And so then we need to fix it, right? So first let us recolor via red sibling case. Red sib. Let's zoom in on that. So let me take our tree, paste it over. Let's recolor. So what did I say? I said parent becomes red. Oops, that's a little bit too much red. Sibling becomes black. Now we need to perform what type of rotation? RR rotation. And maybe it might help, you can view this, we're clustered on the right, so we need to perform RR rotation. If we were clustered on the left of nodes, like if we had real, not null nodes on the left, and a null node on the right, we do right rotation. You can use whatever you want that helps you see right rotation, but we're just doing right rotation. So I'm actually probably just going to redraw the tree if that's easier. Right, so 26 is up here, 18 is down here, and then 34 is over here, and 20 is over here. And then we have a null, 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 and a null. Boop, boop. I actually don't like that square. Let's get rid of it. There we go. That's good. It's fine either way, I guess. Yeah. You are 26. You're 20. You're 34. And then you are 18. Okay. I really dislike that 4. Holy frick. It's good enough. Okay. But did this solve our double blackness? Let's see. 1 skip 2, 1 skip 2 3, 1 skip 2 3, 1 skip 2 3, 1 skip, or sorry, 1 skip 2, 1 skip 2 3, 1 skip 2 3, 1 2 3, 1 2 3. So no, this node, which was double black here, is still double black. But what condition is this now? You can see here that we are in black, black, right? Sibling is black. Looking at the tree nodes, remember? We only focus about tree nodes. We only rotate around about tree nodes. I guess because now we're looking at this as a tree nodes. Before, we're looking at this as our tree nodes. And now we have this as our tree nodes. Make this section look a bit more dotted. Now we have this as our tree node. So we're going to do what rotation? Black, black rotation. Why? Because our sibling is... Oh yeah, sorry, our sibling is black and our children are black. It's like, yo, what is that? No, that's just the recoloring that we do. Yeah, so what does red sibling case do? Red sibling case takes the situation with a red sibling and gives us a situation where we can actually perform rotation, where we can actually get rid of double black. Red sibling does not get rid of double black by itself. Oops, I can't do that. So red sibling does not get rid of double black, but what it does do is give us a situation where we can get rid of double black. And that's pretty cool. Let's code a red-black tree. The first thing I'm going to make is a static class node, right? Inside the node, I'm going to have a field int for the data, and a node for the next one, a node for the left child, and then I need a node for the right child. So we can just, when we create it, and sorry, I need one last field in the string for the color. So when we create a node, this dot data should be equal to whatever data we're going to pass in. This dot left should be null, and this dot right should be null. Because whenever we're going to call this constructor is when we're inserting a new node. And when we insert a new node, well, then it obviously doesn't have any children. Now it just got inserted into the tree. But what do we say about inserted nodes? That they are going to be red. So let's create a public void insert. Insert will take a value of some data, and then it'll insert that. So we can see, let's create a node root. Let's just assign it to null. I'm going to say root. So if root is equal to null, then I want root to be equal to the call of insert node, and then where we want it to be inserted at null, or I guess at root, and I want to pass in the data. Else, we're going to run the same. So I guess you could just make it the same. You could just make it one line. Root is equal to root or insert node, comma data. If the root doesn't exist, then this will be null and life will move on. If the root does exist, then we'll insert the tree, yada yada yada, but the node at the root will still be the node at the root, because that won't change. And thus our tree will be good. So let's create then that public node insert node function. It's going to take in a node called n, and it's going to take in something with data. So it's going to have est properties. So if n dot data is less than the current data, then I want n dot left to be equal to, or no, this should be n dot right is equal to the insert node. So we're going to try and insert the node at the right position. So recursion, this is actual insertion thing. We'll keep it kind of abstract right now and just call it insert node. Then actually define it a little bit later in the code. So then if the data at the node is bigger than the data we're trying to pass in, then that means we should have this node, or the node with this int data, as our left child. And then let's just return n, like normal. I want to say if n is equal to null, let us return a new node of data. Anyway, I want to pass in color, string color. So typically we're going to insert it as red, right? And let me just make root is the node. So root.color will be black. I'll find that there. I guess I don't need this. I'm going to keep it though, because I like it. Okay, let's do this code. If n.color is so, if n.left child dot color, or sorry, n.left dot color dot equals red, and n.left dot color dot equals red, and our left node is red, then we have that double red situation. And that's when, especially when you check the uncle. So the uncle is going to be node uncle is equal to n dot right. If uncle dot color dot equals red, then let's do just normal red uncle procedure. So uncle dot color equals black, n dot color, or n dot left dot color equals black, and then n dot color equals red. Else I need to perform left rotation on n, and we'll just have that back to. So basically what this is gonna do is gonna shift our tree around, and because n is like the parent, essentially, it's in the recursion hierarchy, like n is here, and then children are here, and then here, and then here, right? By changing this around and assigning it back to n, we're successfully modifying this portion of the code. Right? Like I said, rotation, or in recursion in general, you can just write code like this and trust that the actual properties will come in later. Right? Thus we can write code like this and we can trust that LL rotation will be implemented. later, and stuff. The functionality of our code will work. So I'll set this up right now, or we can. I'll set it up. We'll set this up right now. So public node LL rotation, and so I'm gonna take, and this should be node n. So in left rotation, we move the tree this way. So the child of n becomes a new, and the new parent and such. So I'm gonna say the n dot right child dot right. So let's do some. Let's say node. I'll call this one the sibling n. Say node child n, or I'll call this parent. Parent dot left, and then you say that if parent. No, I don't need to say that. So I'm just gonna have some a child node and a parent node, and this should be in itself. So parent dot. Wait, let me actually understand what I'm writing. That's the LL rotation because, right, in LL rotation we said the pattern was this. A tree that looks like this, values tree 2 and 1. We come with a tree that looks like this, values 2, 1, tree. So all we need to do here is really just change this formation. But then we could also have a displaced child like this guy here. He'll get displaced. He needs a place to go, right? Because we've reassigned 2's right child to point to 1. But this, I'll call it 4, is the, I guess you can't see it right now, but I'll call this a star. This is the in order predecessor of 1. Thus, we can safely assign it to its left child. But you already know this because you watched the UILCS video. You don't need me to review rotation. But as you can see, then those are the only two things we have to set up. Nothing about the child even actually matters in this. I can delete that. So that's that case handled. Let's do else if n dot, or here I'll do this, if n dot left dot color that equals and n dot left dot right dot color that equals red. So node uncle is gonna be n dot left, and if uncle dot color that equals red, uncle dot color is black, n dot left dot color is equal to black, n dot color is equal to red. Else we need to perform and the LR rotation. We're going left and then we're going right. An LR rotation of n is going to be this. It's going to be two functions. So public node LR rotation node n. I can explain to you what's going to happen here. So an LR rotation, a tree will look like this. So in a way to look at it is we do perform RR rotation for this section, right? to get the tree to look like this, and then from here we perform LL rotation on this whole section. We get a final tree that would look something like this. It's composed of two of the types of rotations that we have. So I'm just going to say, and what is this? Where does this rotation start? It starts at the left node. RR rotation, right? We said will contain these two nodes, so it's just left and so on. I'm going to say that n dot left is equal to RR rotation, n dot left. And then I'm going to return LL rotation on M. Of course, then this means we need to make an RR rotation. So RR rotation, its parent needs to be moved to what? You know that, or well, this is just defining some basic stuff. So then we do in this, we set the parent dot left node to be N as we shift everything like that, and then N dot right needs to be equal to displaced. Because our displaced node or parent dot left is the in-order successor of our old grandparent. That's why we do like that. I'm just going to turn N. And then I'm just going to say if n dot right dot color dot equals red, and n dot right dot color dot equals red. Oh, oops, I forgot to do this. Then node uncle equals n dot left if uncle dot color dot equals red. Oh yeah, I forgot to. We're gonna have to do coloring instead the rotation themselves for black uncle case. Uncle dot color equals black, and right dot color child is gonna be black as well, and then n dot color is red. Else n is gonna be equal to r rotation of n. And then I'm just gonna copy you, so we don't have to change much. We have to make this say left, but you're gonna say the same. You're gonna say the same, but you need to be r rotation. And we don't have r rotation, right? Let's create it. Public node r rotation. So node n. It'll be the same idea. So n dot right equals r rotation. It's basically the same concept that I explained for LR rotation. You perform LL rotation on the right subtree, and then you perform RR rotation on the whole tree that we're looking at. So the last thing I need to do, and you're kind of seeing it from this error, that the fact that we need to actually update some colors. Okay, so let's add in the rotation. So for all of these rotation cases, we have to do is just do parent dot color equals black, and dot color equals red. And I add that for our rotation as well. Oh, this should be end dot right. My fault. And these should end dot left. Okay, so what we need to do now is update black height. So black height will increase whenever a node switches colors. So when a node goes from red to black, its black height should increase by 1. Thus here, uncle dot black height Oh, we don't have that property. I should add block height. It's an important property for everything in block height. And I'll have a start at 0. So when a node is created, it has block height of 0. So basically, a node block height is going to be equal to the, I'll do it like this, map.max and left block height, comma, and right block height minus 1. Because as you go up the tree, your block height is supposed to decrease. As you go down the tree, your block height is supposed to increase. But other than that, I'm not going to change that much. I don't think I have to worry about all that. And then this then should be our insertion. There's something I'm missing in Loki. Yeah, this is pretty obvious. Because these rotations are supposed to return the new like root node, right? Because or like I guess grandparent, whatever you want. Top of the they're supposed to return this guy, right? Top of the tree, top of the subtree section that we're looking at, the big guy, right? But if I make it return n after we do rotation, that's not what's going to happen, because in every rotation, well, for RR and left left, it's really just the two rotation cases that occur. The parent node becomes the new big boss, big top of the tree guy, right? Look, that's the parent node. That's the parent node, right? This goes here. So by returning this, our n, we're returning here, which is not good. We want to be returning the parent. We want to keep our information consistent. Thus, I'm going to make this return parent, and then this return parent. And one other thing I saw is just the idea of like, I mean, I'm not really checking over here if these nodes exist. Something I did kind of think about, right? It's kind of cumbersome to have a bunch of statements that say, oh, it's this node existing and stuff. But what I can do is just create a public private boolean is red. We're taking a node n. It'll say, so return n is not equal to null, and color equals red. That way, if the node doesn't exist, then we're fine. So I'll go up to the first instance of this, and I'll say is red and dot left. Why are we tweaking? And then there should be n dot left. So is red and dot left. Copy this general structure for you as well. But you should be n dot left dot right, because you're left right rotation. I'll copy this general structure for you as well. I'll make you right, and I'll make you right. And I'll copy this general structure again, but instead of right right, it should be right left, because we do right left rotation. Oh, you're right. Oh, I'm a silly goose, because think about it. Yeah, okay, sorry. Oh yeah, I made a mistake here. I literally was saying that the black height should increase as you go up, and I made it -1, which is stupid because the whole thing in recursion is you go to the bottom and you work your way up. That's what the recursion is. That's when all this code comes into play. You working your way up. So if I'm working my way up, I should be adding one. And then I'm just gonna loop this in and left and in and right. At least I can't just say that it's not equal to null. Because these need to exist, otherwise we're gonna have some problems. And I also forgot to do the is red stuff for the uncle, because the uncle just not exist. right? Your n dot left could just be null. You know what I mean? So if null pointers, I look you be forgetting them. You shouldn't. It's bad practice. They will appear. Are there always something you should consider when programming? Can this node ever be null, and if so, how can I efficiently take care of that? First, that's like the whole purpose of an optional, but that's more Java A than data structure. And I don't think that we need to do this. I'm gonna make these all else ifs, just because I only want one of these to run at least at a time. And I don't think we'll be in a situation where multiple of them could ever run. Like, but just in case, you never know, right? Okay, wait, I want to rework this black height calculation. So black height should be equal to our n dot left dot black height or n dot right dot black height, and then if n dot color is black, right? We said black nodes contribute to the black height, so then it makes sense that we increment this by 1. But then what if these don't exist? What do we do? Is not equal to null. Cool. Let's do n dot left dot black height. Otherwise, let's do 0. And I'll copy u for u. But instead of me talking about this left, I'll talk about this right. And that's how I handle our black height calculations, right? We'll take the maximum of our children, and then if it's black itself, which means it's probably been converted black because nodes are inserted red. Yeah, there you go. That confirms why we're increasing our black height if this node is black. Because of the fact that nodes are inserted as red, that means that there has to have been some change in the tree to make this n a black node, and therefore its black height should increase. It did not initially start off as black and stayed black or something. That's only the root, and the root has a black height of 0. So that is insertion. Let's focus our efforts on deletion now. So public void remove int data is going to take in the, so we're going to return remove node of data starting at root, and then if root is equal to null, just return null. Otherwise, just call remove node, and I'll have this return. I usually have this return a node. I want this to return an int. So let's take whatever node gets returned by here and let's just return its data. So I'm going to create public node remove node. It'll take in a node n, we'll take in a field for its data. So we need to basically do a loop. Or no, we'll just do what we did for the addition, where we'll just go down the tree because then it'll be easy to fix stuff on the way up. I'm not going to do a loop. I'm going to do it like this. That means it wasn't found. Okay, let's get to work. So what I need to do for this method is I'll add in my return n here at the bottom. And then what I want to just do is if n.data is bigger than data, then we need to remove from the left side. We're gonna take a node from here that has this value data. Else if n.data is less than data. Now we need to remove from the right side. So let's just take this chunk from the right side. Else. It's going to be the default case. And then if n is equal to null. So that means we've looped down the entire tree and we didn't find a single thing. Return -1 or return null. We'll take node n, so you can remove node data, root comma data. If n is equal to null, return -1. Otherwise, let's return n dot data. I'm just going to chunk this into my sections. There's 4 lines. I like this one because I really like that. Okay, so let's do this now. So with deletion, first we need to code in the red or normal binary search tree deletion. So else and that data is equal to data. Just assume, but I just like writing it. Or I'll do else if then to make me happy. Fine. Fine, it was right here. This second bit will run when we found it. Or no, let's put it in here because when we actually find a node, when you see the node has no children, then I can just simply set n equals null, and this will kill it from the tree. And therefore, wherever it came from, we'll have a pointer pointing null. One child, and let's just set n is equal to if n dot left is not equal to null, and n dot right is equal to null, and it's going to be equal to n dot else if n dot left is equal to null, and n dot right is not equal to null, and right is going to be equal to and sorry, this would be if n dot left is equal to null and n dot right is equal to null, then n can be null. N will be null. Then we'll return n to avoid any errors. So n is, we're going to return null just to show that the null doesn't exist. Here we'll return n. Then here we'll return that. Else we have 2 children. Oops, did not need to do all of that. So 2 children. I need to get the predecessor. So I'll just do inner predecessor. So let's create a public node get pred in order predecessor. In order predecessor is n is equal to n dot left, and while n dot left is not, n dot right is not equal to null. N is equal to n dot right. And then once we set final one, let's return n. That's gonna get us our predecessor. So I'm gonna say because what we need to do is we need to swap with our inner predecessor essentially, and then wherever our inner predecessor was, we need to delete. So n dot data is going to be equal to get inner predecessor of n dot data. and then we need to kill it now. So let's just say that n dot left is equal to remove node get in order predecessors, or n dot left comma get in order predecessor n dot data. So we're gonna hunt it down and kill it, and because it's an in order predecessor for get in order predecessor. I like saying get in order predecessor. That doesn't, you know what I mean. So this is the normal deletion that we talked about. Now we can just do this. So firstly, if there are no children, that means that actually, well, let's go in order of the cases that we discussed. So the first case was deleted node is black, sibling is black, and children is black. So this is gonna kill the node, right? Yeah, that's fine. Dandy. But now we need to just do some recoloring outside of the tree. So we're here now in our tree. Okay. So the major difference is we need to return a double black node instead of deleting an old node. And okay, well actually no. If n dot color dot equals black, or I'll do like this. If not is red n. I don't even think we need to do that for this one because it's pretty obvious that we have this node. Else, right? The same idea here. If not is red n, then this will be else. Okay, well this node is red. Let's think about it. So this is a scenario where we have a tree that looks like this. Some child here, and we're leading this guy. So then the tree will look like this. If this one is black, and then this one is black, then we let them black. If this one is red, we can just set it to be black, and then I'll solve the double black. So if is red, excuse me, and dot left in this case, then n is equal to n dot left, n dot color is equal to red, is equal to black. I'll take care of the black there, and we can copy you, or all of you really, for the second case with the right. I said I'll make this right, and I'll make this right, and I'll make this right. And then this is my bad. I want to store predecessor as a variable because it could change. Get in order predecessor might be different depending on the end or depending on which stage in the recursion we're on. I'll just call it like this. But of course, we don't have to actually do anything here because it's gonna set whichever node it removes to be double black anyways. Right? Or let's think about this actually. If I have a tree that looks like this, you, and I'm gonna delete you. I'm deleting you, right? So you're going away. And you are black. And you're red. And you're black. But we're not gonna take the black node up. That's gonna create a double black error. We'd rather take the spread node up and then make it black. That means it's not only good to have get in order predecessor, but I might want to get in order successor. Node goes equally get in order successor n if, or I'll call this suck, if pre dot color is equal, if is red pre, then let us swap it. Right? And then say n dot color is equal to black. I don't think the color will change of n, but just ensure it won't. But excuse me, just ensure. Else if is red suck, then n dot data is equal to suck dot data, n dot right is equal to remove node n dot right comma suck dot data, and then n dot color will be black. So then we're good and life is good. Else, this means they both are black. Let's just run this, I guess. But let's set n dot color to be double black. So now that we have some coloring built in, if I just go out here, I say if, because we're not actually getting rid of it. So if I say that n dot color dot equals double black, then that means we need to go to our cases. This means we identified that we have a double black node in the tree. This is the problem. How are we going to fix it? First method is to look at this. So actually, I want to just, let's create another helper method. I'll call it is double black. So it'll be like private boolean is double black node n, and it'll be like it return n is not equal to null, and n dot color dot equals double. So here I'll say if is double black n. Well, not n, because we're looking at it from a parent point of view, right? So this should be n dot left. If n dot left is a double black, and n dot right dot and is not is red. Right here, let's just leave it like this for now. If not is red and dot right, and then if not is red dot right dot left, and not is red and dot left dot and dot right, then we are in a black case. And in this case, we take the sibling, which would be n dot right dot color, we set dot color equal to red, and then I'm going to say that if n dot color dot equals red, and dot color dot we'll set it equal to black, else if it's black, n dot color should equal double black, like that. And there's none of this my double black. It's just a space. Or I'm just gonna make it a space like this. Double black. Okay. So that's that case. The other possibility for left is we have one child is black and one child is red. So that's gonna look like else if n dot right dot left So I'll just say else if is red and dot right dot left. This. First, we need to perform RR rotation. Upon what? We perform RR rotation upon this like branch of the tree. So I'll say n is equal to u, and then or well actually this would be RL rotation because our tree's a little bit busted, right? We're going right and we're going right left. We'll do RL rotation. And it'll be a specific removal because colors are unique in this. And we can then worry about the coloring and stuff inside of this rotation. So let's worry about that, I guess. Let me find removal. RL rotation here. I'm gonna need all of this, I guess. I'll just copy this much, or I'll go up. Let me take the 4 rotation methods that we have, because this was cool enough for insertion, right? This was cool for insertion. Everything was right for insertion, but I said that recoloring is different for removal. I'm gonna call this removal, and then removal, and it's gonna call removal. It's gonna call removal, like that. Okay. So it's gonna be like normal, right? Except in terms of coloring, we can say that the sibling will take its old parent's color. So what would that be? Where's our sibling right now? If our tree looked like this, and I deleted this node, and then this node was red and the rest are black, and then we flattened it out to look like this. So RL rotation will make you go here, make you go here, and then we're rotating this way. Then instead of just being called parent, I'll call it sibling. Yeah, you'll be called sibling, and then child will be n dot right dot right. Okay, yeah, we got this. Wherever I see this, I'll call you this. Wherever I see this, I'll call you this. Wherever I see this, I'll call you this. Node displaced sibling dot left. Right, it's just normal. Except sibling dot color will take the color of the parent, which is n. So you have to become n dot color. Then n dot color should be black. And then lastly, old child's color. Oops, a little too far there. So child dot color should be black. So that'll handle that. That'll remove the double black stuff. So we're good for that. So this is the red child case. Now, so if this is false, else else means that we do have a red child, a red sibling, so we have to do the red sibling case. So the red sibling case, I said we perform rotation towards the deleted node, and then we just recolor. So in this case, because our sibling is right and deleting the left node, I'm going to do remove. I'm just going to perform removal RR rotation. I also call this red sibling removal RR rotation. Oh, this is gonna get messy really fast. I don't know, because the way we could do it is just update the settings and stuff, or the let's see, should I just do that? Because I'm already creating more and more. Let's just do normal removal RR rotation. I'll keep the two that I already had, the two different types. Let's run this. Nah, you know what, let's make it. I feel like it'll be a little bit more easier to understand if it exists. So these ones and then there's gonna be red sibling RRR rotation, which is what's gonna be called right here. Well, actually, no. This will be called if. Okay, yeah. So we'll perform red, right rotation, and then I shall delete red sibling RL, and I shall delete red sibling. Oh, I don't think. Yeah, here. There we go. There we go. So if you handle these else's, what if else if is red and dot right and it's equal to removal RRN, so we're just gonna call it straight up. Else if is double black and dot right, if not is red and dot left. This means we don't have a red sibling, and then if not is red, it's children. So I'm just doing, it's gonna be black case, just for the left side. Black case and dot left dot color set equal to red. Right, that's what we said in black case. The sibling gets recolored red, and then we need to push the blackness up to the parent. So if we are red, then we're good, and I can just say that n dot color is equal to black. Otherwise, if we aren't black, and in fact we're sorry, if the parent is black and not red, if we try to push the blackness up to it, it won't do much, right? because it's already black, so we'll just have another double black there. And then else if is red and dot left dot right. Let's perform n is equal to removal r and lr rotation. And I'll fix this and make a camel case soon. And then else n is equal to removal ll rotation. And else, or well, I don't like jumping ahead of the gun. Let's set up LR and LLR. Excuse me. Excuse me. So removal LL rotation is going to follow the same idea as removal RR rotation. So in this one we said that let's just fix some things around. It's going to become the sibling. I'm going to need a node for the child. It's going to be equal to sibling dot right. Whoa. No. This is sibling dot left. And then this is sibling dot right. So where I see parent, I'm going to make that sibling. Excuse me. And then we said sibling will take on the color of its parent, so n dot color. Then of course the old parent will become black. And then the child dot color is gonna become black as well. And that's not how you spell child. This is how you spell child. Does that match up what I said here? Yep, as it should, because it's basically the same idea. And then just remove LL or LR is good, so this is all good. That's all set up. So now we need to do the red sibling case. So I'll just write that here. So else n is equal to red sibling LL rotation with the node n. So we even have that defined. Yes, it's set up right here. Let's do the stuff that we did before we named the variables once more. Is that a bar? There we go. We don't need child for this because in a red sibling, well, you can just see the color change that we do here. Oh, I guess it's just the exact same as in the normal insertion. Maybe, alright. So in this, all of its methods and such should be the removal tree or the removal method. So I'm adding this return n because basically we don't want to go into the two children case. Or actually, you know the easiest way for me to fix this? That's what I did in my binary search tree video. If n dot left is not equal to null and n dot right is not equal to null, then let's just yoink. And then I also forgot, I got a little bit carried away. So if is red is not, if this is false, then we actually have a double black situation. So I'll set n is equal to n dot right, of course, but then n dot color should be equal to double black. I remembered this, like I think I explained this, but I just forgot to write it in our actual implementation. This should be in the left. And then also over here, I was being a bum. I literally explained in the video that red sibling does not fix anything. Now we have to, I guess we look at this. But hey, if we have to call this again, then that means let's take all of our code here. Give me you. And I'm just going to create a public, a private, I guess void. handle double black, taking a node n, and it'll run all of the code that we had on it. And then here, let's handle double black n. Or actually, I want to maybe write this n dot left is equal to, watch. Wait, let me cook. I have a recursive. My brain is just saying that's how it's supposed to be done. And let's see. Mm, 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 yeah, and right is equal to b for your n dot right portion. Because I don't think we need to subdivide this somehow. And then so return the node to do all that fancy stuff, fancy. And then I'll run if is double black n dot left. Do this. If is double black and right. Do this, but make it for the right side. And that should be that. Wait a minute, I'm literally a buffoon, bro. Why am I doing n dot left for this section at the top? That doesn't make sense. If is double black n dot left. The reason why it doesn't make sense is because we run the same line down here. So I feel like it makes more sense to say n is equal to handle double black n like this. And then I also realized we don't have a return. Yeah, that's probably that's why this is red, right? Yeah, let's return n here. And then the last check we need to do is if is double black root. So if we've made it so root is not equal to null and is double black, well that takes care of itself. Then let's just say that and let's say and n is equal to root, then n dot color is equal to black. Because there is a possibility where if this double blackness propagates up the entire tree, maybe like we delete the second to last node. The last thing I want to do is fix this remove method. So I'm gonna run say that if first of all if root is equal to null, return null. And then we're gonna run node and is equal to return false, sorry. N is gonna be equal to node root comma data. So we're just gonna run the remove method and such, right? And then update our tree accordingly. Just say root dot color. Let's ensure that it's black. We don't need to do that. It's probably it should just be black anyways. But just in case, because we did see actually it's a good thing to add because we did see times in the demonstration or example part where I was on paint where we'd have to manually update that to be black just to make sure the tree still worked. Or that rule 2 was still met. And then I want to make sure basically if this data is not in a tree anymore, or let's do it here, right? We need a way to basically say if the data that we're looking for is not even a part of the tree, return false, which means we need like a search method. I'm gonna call it contain. So we're gonna say if this contains data. So if it doesn't contain data, I want us to return false. So the data is contained, and then this was run, and that means that the node exists and was removed. Alright, so what I have to do, we have to create this remove method. So I'll say public void contains public boolean contains data. Now let's take in the node. So I'll say node and comma data. Say if n dot data is equal to data, return true. Make this an int. If n dot data is less than the data, then we're gonna run contains on n dot right comma data. Else we need to do contains n dot left comma data. After all this, if it's still not found, let's just return false. And also, if right here, right, we're updating this, there could be a universe where root becomes null. And if root is null, it's black. We won't be able to access the color. Let's just do that, just in case. Because you don't know what happens. What if we remove the root node or something, right? Then root will be null. So this should be a completed red-black tree. Okay, so what we can say is if n is equal to null, return false. And so basically we've gone through all of this, or we've gone through it. Okay, we've reached the end of our right branch. We haven't found it. Let's just return false. Maybe let's try this. Oh, we still haven't found it. Okay, it must not exist. Let's just return false. This and here and such. Because we're saying that basically this can return false if n dot right is non-existent, and then here we're trying to access the left property of right n dot right. But this, sorry, yeah, let me explain it better. So this will say that basically when is red is false, this will be true when this will go here, but is red can be false when n dot right doesn't exist. So this is n dot right doesn't exist, this will evaluate the true and will go here, but then we're immediately accessing an element on n dot right. This means we need to check n dot right is not equal to null, and then we can just leave it like that. And then down here I'll add n dot left is not equal to null. So I can just add this to you as well. And then I'll just go up here and I'll add you to you as well, and then to you. I guess make you the else. Another problem we have is with this removal. This should be an else if of you. Because what might happen is that, and I'll make this just, it's gonna tell me to delete it, right? Yeah. And it's gonna tell me to delete this, exactly. But what the reason why we have to make this as a if else system is because we're talking about the same n, and if I made that an if, what's gonna happen is, let's say this code ran, then n is gonna be updated, right? N really gets updated, and then what if that node has two children? Then we're gonna delete that here? No, it should be one or the other, not this and then oh let's run this. Okay. So with those minor issues out of the way, that is the red-black tree. Everything should work. It should be good now with the code. Surprisingly, it wasn't that bad. I thought it'd be worse. Yeah, let's go, guys. That's the red-black tree. It's a little bit more difficult to learn. We walked through the code. We went through it. Hopefully, you understand the cases. And yeah, thank you for watching.